If you are the owner of an oscilloscope with basic facilities, it's highly likely that if you start looking at waveforms or slow voltage level changes, then this is typical of how the trace will appear on your screen. Not particularly useful if you want to examine the quality of the waveform, for example. In order to improve upon this, you'll need to either buy a better scope or simply make yourself an add-on device to achieve the same goal at hopefully a fraction of the price. This video is the fourth in the series covering the 6502 8-bit microprocessor from grassroots level upwards. In our previous videos, we finished with a simple working single board 6502 computer which was driving a DL1414 intelligent display. In this video, we'll be taking the exact same board I made for the series and adding a further 4 ICs to giving us the facility to view low frequency waveforms on a rolling display which is easily viewable on your existing oscilloscope. I'm planning to use this circuit myself to give some more useful functions for my own usage, but felt it would be helpful to stop at this point and make a short video detailing all the basic requirements for somebody who might need to make a version of their own. Once again, this is working correctly, but it's up to the builder to decide if they wish to expand the program itself and the hardware perhaps to include additional features or settings. In order to make a low-cost project, it's a good idea to choose readily available and inexpensive ICs for the A to D and D to A converters. Both are 8-bit devices, which could do more by making small changes to the programming to include additional analog inputs or completely separate analog outputs. The interfacing circuit is included at the end of this video along with another copy of the 6502 SBC as given in our first videos. It's important to note that the circuit as it stands must be treated with care as there's no protection on the A to D input. Therefore it might be easy to damage it with no overvoltage or overload if no attenuators and basic protection circuitry are included in the final circuit. To demonstrate the device, I've knocked up a simple low frequency test oscillator using an 8038 waveform generator IC. It's a useful and versatile IC, but not terribly good on the sine wave output. It's certainly good enough for us to see here for this demonstration, enable us to see the waveform limitations even at these very low frequencies. A quick few words about the program I'm using here in the demo. First and foremost, I'm sure there are programmers out there who could do a better job than me, but please bear in mind I wrote this in machine code for myself. So you can see the basic listing is quite straightforward. The first part clears the memory to be used. The second part being a single A to D read routine, with the third actually reading out the current values in the memory before sending these to the D to A converter for the oscilloscope input. The last two subroutines are just delays. The first is a 1 millisecond, a delay between starting the A to D, which actually then lets you read the result 1 millisecond afterwards. It would then be quicker to use interrupts, I accept that, but speed was not the essence, therefore I chose this approach as it's easier. Second delay is approximately 11 milliseconds with the chosen clock speeds, but can be altered to vary the speed of the read. I've written two prompts to show the difference between the 11 millisecond delay and a slower variant to display about twice as many transitions, we call them, on the same length of line on the scope. I've included a few blocks of NOPs throughout the program. There's a no ops, as I always like to make it easier to add more code myself without having to rewrite the whole thing over multiple times and recalculate any absolute and relative jumps that might be affected. Whilst this code listing does show the prom locations for the programming purposes starting at 4 zeros, and ending in 07FF, the actual prom itself is located at the top of the memory map. This means that the actual start location is really F800. The prom I'm using here is only 2K with another 2K used for the RAM. Lastly, don't forget to put in those two reset vector steps at the prom locations 00FC and 00FD. Here you can see the output of the oscillator. This is the best we can actually see on the scope. We're not feeding it in yet to the device here. This is just simply a pot on the input to attenuate it a little bit. So hopefully if I disconnect this piece from here, I'll disconnect the probe from that, and we connect it to the output of the device. Let's move the shift position up, and of course change the time base, and that is the result. We turn the attenuation down a little bit. Oops, I have to lift him up a bit. That's it, there's nothing going into it at all, and gradually as we bring that up, there we go. If we now shift the clip from there to the triangle wave output, we now have a triangle wave. There is in fact a square wave somewhere along the line, but the level's different, so I'll try that. Oops, there we go. And that is the square wave. Might need to adjust the sync slightly. What it's doing is interfering with the sync pulse we're generating. So, oops, there we go, attenuated a little bit. So obviously there's a sync pulse generating for the scope to trigger on, and that was affecting it because it was coming up on the same level. That's why there was that jumping there. I'll change the EEPROM and use the other version, which should give us twice as many on here. And this is changing the timing of the, if you remember, there are two subroutines. One is a fast subroutine and one is a slower subroutine. It's flickering a lot more. You can see we're seeing twice as many characters on the screen as we had before. Obviously it wasn't designed to be run at this speed, that's why it's flickering a lot more, because it's not a very efficient use of the trace on the scope. But there you go. Let's go back to the sine wave. Oops, I'll do this one a bit tight. That is off. And this should be our sine wave. There we go. One project which is quite straightforward and easy to make with just 4 extra ICs on this circuit here. I'll put up the circuit diagrams right after this video, and any questions, don't forget, put them in the questions below. Thanks for watching.